So today I'm going to discuss how we could easily implement a DFA in software. So let's say one way to do it is that we could have a table which has rows and columns, a two-dimensional table. And let's say the rows are all the states, s0.sn, and the columns are all the possible inputs that belong to your character set, sigma. Now the table is formed as follows, that if the DFA transitions to state S2 on input X2 when it was at state S0, then I just write S2 in the corresponding cell, right? So let's say if I'm in S1 and I get input X2 and then I go to S0, then that's what this particular entry here represents, and so on. So basically the entry stored in the table in the two-dimensional array is basically represents the next state for that particular state comma input character pair. Right? With this representation of a DFA, it's easy to write a DFA execution code. Well, I'll just start my I will start my counter I, which indicates how many input characters I've already consumed. I'm going to start my initial state. In this case, I assume that S0 is the initial state. So I start my initial state at S0. And then I just consume characters while input I state equals T, which is a table. And it looks at the state comma input ith element in that state, and just updates state with that. Right? So let's say I started with state S0 and I got input X2. Then I'm going to say state equals T X0 S2 X2, and recall what was T X0 S0 X2. It was S2, so state will become S2. And in my next entry, I'm going to say what is state S2 and what is the next input, and so on. And I'll keep doing this until there's input I. So I'm assuming that when input I is 0 or the null character, then I'm done with the input. So it's a string of inputs, right? A string of input characters. All right, so this is a very simple way of implementing a DFA in software. This is linear time in the size of the input. It requires two memory accesses, one to read the input and the other to actually read the table. There are, but there is one problem with this, potential problem with this implementation. It's the size of the table. So if the number of states in your DFA is very large, or if the input character set is very large, then the size of the table can become really large as well. And there are some optimizations that you could perform here. For example, you could deduplicate identical rows. That's actually usually a very significant optimization when we are talking about DFAs that are used to Lex inputs, because some states are going to do identical things or for identical inputs and things like that. All right, so that's the DFA execution code. There is also another possibility that instead of using a DFA execution code, you could have used an NFA execution code, which means that instead of representing your state machine as a DFA, you could have represented it as an NFA. Recall that a DFA could be larger than an NFA. Recall that a DFA state in a DFA was formed by taking a subset of the states in the NFA. And so it also means that a DFA could be exponentially larger in the number of states than the original NFA, which represented the Lexing logic, right? Because there's an exponential number of subsets for a given set of states, right? And so the size of a DFA could be at most exponentially large compared to an NFA, although in practice it's much smaller than exponential blow up. In any case, it is possible to also simulate an NFA in software in a similar way. If it is an NFA, then it is possible that when you are on a state, it is possible that for the same input you can be in either of the other states. So because it's non-deterministic, and to represent that, you could have a table which stores a list or a set of possible next states. And so the loop in this case is just going to maintain not just a single state, but a set of possible states that the NFA could be in. And then it's going to look up the corresponding table entries for every input to decide what are the next set of states and so on. This is just like, it's almost like saying that we are converting the NFA to a DFA on the fly, but in a very input specific way. And in this particular implementation, it is typically more space efficient because the NFA number of states would be smaller than the number of states in the DFA. So it will be more space efficient, but it will take slightly more time because you have to maintain now a list of states rather than a set of states rather than a single state, as it was possible to do for the DFA implementation. In practice, lexers or lexical analysis tools give the user the choice to choose between a DFA implementation and an NFA implementation, and the user can pick one of them depending on whether space is more important or time is more important.